Thanks, everyone. Thanks for having me today. So the topic of this talk is scalability. Whenever we think about scalability, we think of something like this. A big-ass architecture that has loads of boxes, that looks really good on a whiteboard or on a big diagram. But in reality, there are a lot of other things that are as important as the architecture. And we tend to neglect those other things. So in this talk, I'm going to talk about the other soft skills and topics around scalability. And if you want specific technical content, I'll be happy to talk about it maybe later. Just grab me and I can go on for hours. So what I learned in these years is that scalability is not just about technology, but it starts from two other very important building blocks. That is people and processes. So in most successful companies and startups, usually are not those who made the perfect right decisions, technical decisions from the start, but rather those who focused on company culture and people and processes. And eventually, those took them to the place they wanted to be. So people, let's start from them, how to get them, so the hiring process. Whenever I hire someone, I usually think about learning from that person. So I tend to hire people that are smarter than me, because I don't want to work with someone who I can't learn anything from. So learn absolutely really brilliant people as a rule. Also, try and find good people that you are focused, driven, and can take on any kind of challenges. But also people who don't despise doing less glamorous tasks when they are needed. So promote fun in your working environment. This is so important, because engineers work on really hard problems. They really work hard on tough challenges, but they also want to enjoy themselves. They like being in an environment that helps them also distract themselves. This aspect of culture has really the most profound impact on scaling the team. Likewise, beware of toxic people. So during the interview, pay attention to the character of people, not just to their skill sets, because a bad character can really ruin your team from within. I usually do the Sunday afternoon or Saturday afternoon test. That is, I think, if I am to go to the office on a Saturday afternoon or a Sunday afternoon, and I'm alone with this other person, would I enjoy my time there with that person or not? And the answer usually can tell me whether I want to hire that person or not. Beware, it doesn't matter if they are geniuses. If they don't work hard or they are a bad character, you're better off without them. Another thing is that engineers that learn and adapt are 10,000 better than experts in a specific framework or in a specific technology. Because technologies come and go. So you might invest a lot of your time, resources on Cassandra or React or another specific database technology, for instance, and you might want to hire people who can know how to deal with them. But if 6 months down the line, you realize that that was not the correct technical choice for your architecture, then you get stuck with people who can only do that thing. I've seen a lot of presentations already this morning about scaling teams and the good practices in managing teams, in implementing agile techniques. So I will skip all that. I'll just mention something about the teams. Well, first of all, the size of the team is very important. Because if the size of the team is too small, you can't really achieve much. You tend to micromanage people because you have an impression that they are not doing much, so you tend to stand behind their shoulders all the time. But reality is they're just too few to actually do a lot of work. So a good size is usually 5 to 7 people. 6 is the sweet spot. Also, never make the mistake of organizing teams around skill sets or languages, because that creates artificial boundaries in your team that are really, really tough to tear down. And usually that creates a lot of conflict within the company on who's the best team, rather than having the whole company focused on the success of common goals. So a suggestion that I tried and experimented with and worked really well was to have cross-functional teams. So whenever I had a new feature to implement, what I did was to take 1 or 2 people from each department effectively. So 1 or 2 engineers, 1 tester, 1 DevOps. So you bring in people from different backgrounds who can take different parts of the project on themselves, and then you let them work together from the start, so they all work as a team towards the common goal. So this is really working well, I think. So no more about people. The second part of scalability is processes. So why are they critical? I can think of 3 main reasons. So first of all is they standardize everything that is repetitive. You don't want to think about repetitive things all the time, or had to be slightly annoyed because different people do the same things slightly differently. So it's better to standardize those repetitive things. Also, they help reducing the mundane decisions, so we can save our brain cycles to really important decisions. So we can focus not on trivia, but on real problems. And finally, when you are in a crisis, so when you tend to panic, having a script to follow, some process to follow, help immensely, both in finding the problem fast enough and also resolving it. I wouldn't suggest implementing too many processes, right? If you're a startup, and you're small and you don't want to be bogged down by processes for the sake of them. So just implement the right amount, the right process at the right time. And because good processes can really help your company scale, but you don't want them hinder the productivity or demotivate people. So let's see a couple of them that are really crucial for scalability. One is whenever you need to scale, whenever you're at that dreadful moment when you have too many users for your current system, then instead of immediately thinking about which database to use instead of the current one, or which messaging system to use, stop for a moment and measure your current system. You need to know where you are starting from in order to get somewhere else. So this is a process called Headroom, or capacity planning. It's very important. It affects every single component in your system. So you have to know how much CPU you need, and how much you think you'll need in 6 months. You need to think about storage. You need to think about bandwidth, both internal and external. So think about all the components that make up your architecture, and try to split them down, and one by one think about whether they are a bottleneck right now or they will be in the near future. This is important for a number of reasons. First of all, budgeting. If you have a fixed budget for the year, you need to know how to spend it. So you need to know where to spend it. Second, same reason, not just computers, servers, but also people. You need to know where your pain point is, whether you don't have enough testers, or you don't have enough engineers, or enough DevOps. Another process that is absolutely crucial if you want a stable product is to control change. We tend to change our system continuously whilst running. We we implement new features, we change the components, and we do all that, but we are a bit reckless when we do it. We don't think about the amount of risk we're willing to take with any given change set. So there are different ways of assessing the risk associated with a change. There is the finger in the air system, which is also known as gut feeling. So one person just comes out with a number, oh, I think this is going to be risk level 5. But of course, that's not very reproducible. It's not even very scientific. There are other systems that are as simple, but are slightly more scientific, like the semaphore approach. So for each feature, for each change you plan to introduce, you have a semaphore, like green, amber, and red. So you assign a light, determining the level of risk on that application. And then you sum all the semaphores, all the lights, to come up with the overall score. So you can understand whether you are actually taking too much risk in one go, or whether it's safe to proceed. Also remember, risk is cumulative. So it's better to introduce features one by one than have a massive change all at once. And people have a different level of tolerance too. So especially when we are pushing things or fixing things in production, we start to think after 2, 3 successful operations, we start to think we are immortal and we can't possibly make any mistakes, and that's where we make the most atrocious mistakes. So always consider how much risk a single person is taking in a certain amount of time. Another interesting process is load and stress testing. They are slightly different in the intent. So load testing is all about measuring your application under the expected load. So you think about your SLA, the guarantees you want to offer to about your service to your customers, and you make sure that your system can handle that kind of load. Stress testing is pushing your system to the limits. And you want to see what happens when your system breaks. So when you're going overboard, over the boundaries. And a couple of things can happen. One, you reach the maximum capacity of your system, and then you have a flat line. So you don't really accept more requests. That's the limit. But your system is stable at that point. It's simply rejecting new requests. Or you can have something horrible like this. So as soon as you start breaking the things, as soon as you're over the top, you have huge spikes in latency, response time, and you don't want that. So this is really dangerous, because it means your application will go down almost immediately after overcoming the threshold you had in mind. So it's much better to break things, but keep the rest of the system stable and have a line like this. So you have some failures, but the system overall is fairly stable after that threshold. There are a lot of open source and testing tools you can use. JMeter is one of the most famous one, or the Grinder is another good one. There are also hardware appliances. I know HP and Aspirant make really good ones, but they cost usually 10, 15K for a single box. So it depends whether you can afford them or not. So what's the goal of processes during development? Well, they are barrier conditions. They prevent you from making stupid mistakes along the way. And there are different ways you can protect your system, your production system, from those mistakes. And it's up to you to set those barriers. And they can take form of a code review to make sure that someone else looked at the code before it goes to production, manual and automated QA tests, usually using some kind of continuous integration system, and doing other tests, even trying the full feature on different environment before going to production. This is true also for the deployment itself. You want to try the deployment process itself on a staging system before going to production. Third part, and probably the most interesting in the presentation, is about technology. So I'm gonna here just to have a carousel of solid principles about scalability on how you should think about architectures if you want your architecture to scale. First of all, the N+1 design. Whatever you do, whatever component you're designing, make sure you design more than one of it. So you should not have any single point of failure. You should always think about distribution of workload from the start. Second, mistakes happen. We can't prevent them. So make sure you have a rollback strategy if you happen to deploy a borked release. Equally important when you deploy a new feature is the ability of disabling it. So this is known as a shadow release. Many companies like Facebook do these kind of soft releases all the time. So they deploy a feature which is either visible to a very small subset of users, so maybe only users in a certain geography can preview the new feature, or even they hide it completely from the user, but trigger the behavior with JavaScript, so they effectively fake the real load that feature would have in production without showing the effects of that feature to users straight away until it's proven that it works under real load. Design to be monitored. This is so important. I'm going to talk tomorrow about monitoring because I believe it's one of the most important features of them all. From the start, you should always think about monitoring your application. It's not enough to add some probes at the very end when you have the feeling that something is not quite right. It's much better to bake in monitoring hooks into your application, into your system from the start, because they can also be extremely useful during the development. Because if you spot that a feature is really heavy on CPU or memory, or creates too many dependencies, so it creates a lot of latency or contention, then you can spot it immediately, even in a dev environment, if you have the correct monitoring infrastructure in place. Design for multiple live sites. Sometimes we think about high availability as having some kind of live and failover configuration. So you have a live site, and then you think whenever things go bad for that live site, you can switch to a hot spot. So you can switch to a failover instance. The idea is not bad, but in practice, it never really works as you would expect, or at least it's not immediate. It takes a long time, usually, to bring up the failover instance, or it's often inconsistent because maybe the data or the sessions haven't been replicated correctly to the other instance before the live system went down. So it's much better to have many live systems all running in different data centers at the same time. And if one goes down, the others should be able to take the additional load. As a side note, if you only have 2 of them, make sure that each of them is at less than 50% capacity, because if one of them goes down and it's taking over 50% of the load, then that 50% of the load will add up to the existing load on the other server, go over capacity, and that the second failover instance will go down immediately as well. This is a bit controversial because as geeks, we like to play with new toys. We like to play with the new technologies. Oh, we see on Hacker News there is a new framework, a new library that promises that will solve every single problem. The pixie powder, as the previous talk mentioned. Reality is you want to let others discover bugs before they bite you. So at the cost of reducing your personal satisfaction and using new technologies, maybe stick to what's safe, because a MySQL database can really do wonders instead of just trying your luck with modern technologies. Asynchronous design is also something you should strive for. Synchronous design means you have to wait for something else to be available to respond before you can continue. So this is one of the biggest limitations to scaling any kind of system. So you should always try and and write asynchronous code and design your components so there is the least amount of dependencies possible. I'll come back to this point in a bit. State is also the enemy of scaling. If you have sessions or any kind of shared state, it means you have one resources that will be extremely contended. So even if you have 1,000 different web servers, but they all rely on a single database for the state, then that database is going to create a big bottleneck. So if you do need the sessions, most of the times you don't, but if you really do need sessions, try to push them to the customer. So use cookies or other techniques to move the bottleneck away. So you can scale the number of users very easily that way, and the state for users very easily that way. Another argument is when to buy and when to build. Again, we tend to be subject to the not invented here syndrome. And we like to build the things, even if there is a perfectly valid option on the market already. Be aware that this can create a massive amount of destruction. So the overall cost over time will probably be the same, if not even greater. And you lose focus. So the time you spend developing that non-core feature could have been spent improving your core feature and differentiating yourself from the rest of the market. Synchronous calls, I mentioned earlier, they limit the scalability of the project because they effectively force you to stick to the slowest link in the chain. So if you don't have synchronous calls anywhere, then it's much, much easier to scale. Also, decoupling things is what you would like to do always. The image here represents swim lanes. So think about swim lanes. They give direction to the swimmer, and at the same time, they protect that swimmer from whatever is outside that lane. So they can go at full speed without having to worry about what happens outside their lane. So this is the optimal condition. If you start adding synchronization checks, so you need to wait for another thread, another process to be available before you can continue, then again, you're back to be limited by the speed of the other component. So swim lanes are great because A, they increase availability. They limit the impact of failures to that single swim lane. So if you have your system divided on different servers, and you have one server for your shopping cart, one for searches, one for your product catalog, if something bad happens on one server, then failures are contained to that server, and it doesn't affect the rest of the platform as a whole. So it's really, really good to have this kind of protection in place. When you have to design swim lanes, always think about what generates more money. So that should be focused first. You don't want the shopping cart to go down ever. If the catalog becomes unavailable for 5 minutes, that's fine, as long as people who are ready to proceed with the checkout can go on. Also, think about features that can be unstable and put those on a separate swim lane so they don't bring the rest of the system down. And finally, think about the natural topology of your service. If you can think about the separation of different features, like I said, the shopping cart, the search system, the product catalog, then that's good. You can have different kinds of topologies. It's not just limited to actual features, but you can think about I don't know, if you have a multi-tenancy environment, like a CMS with different users, or some kind of a shared environment, you can maybe put the clients, one or two clients that cause most of the traffic on a separate set of nodes, and leave the others who put less load on the system on others. So, as just a continuation to what I said about swim lanes, think about swim lanes as just braiding things. You can have like laces, and they are beautiful, clean. But the moment you start adding synchronization or dependencies or any kind of lock, you start complecting things. And complecting things is an enemy of scalability. You should strive with simple, linear paths everywhere. By the way, Rich Hickey, the author of Clojure, gave a wonderful talk on these things. So there is a link down there if you wanted to explore more about this topic. Finally, when you design things, you might be tempted to jump to specific technologies. So whenever I ask someone, please, can you tell me about your technical stack, with your technological stack, I get answers like, oh yeah, we have a Dell firewall, we have a ProLiant server, we have an Oracle database. Well, that's not really what I asked for. That's an implementation. It's not an architecture. So whenever you design things, think about components, not specific implementations. Because this way you can design your system properly. The other way, you risk having vendor lock-in. So you get stuck to what's available for that specific vendor, rather than think about what features your system should have. So if I now ask you how to scale a system, well, you can say, well, you start with people, you start with good people, you follow good processes, and finally, you implement the correct architecture. But there is another way to scale almost indefinitely without even doing work, and it is by caching stuff. So there are different types of caches you can implement. The first one we usually encounter is some kind of object cache that is introduced within your application, and that takes the form of a Memcache or another similar system. So you kind of serialize the results of computation. You send down to a kind of distributed or local cache, and then you retrieve it back when you need it. This means you often have to change the application itself to add these set and get calls. Other types of caches are HTTP caches or proxy caches. They are usually better because you don't have to change the application. If it's a web application, you just use standard HTTP headers to control how that page should be cached. The difference between proxy and reverse proxy can be probably simplified by thinking about a proxy as something that works for an infinite number of sites for a limited number of users. So think about an ISP or university that has a proxy to cache requests coming from that circle, so that set of users, so that set of students, onto the general internet. Reverse proxies are usually closer to an application, so they affect a small number of sites that you control, and they apply to all users. There are a lot of good products. Varnish is probably the most popular choice nowadays. And finally, there is a specific variety of reverse proxies, which is CDNs. So you can effectively copy your static resources onto other geographically distributed areas, and you can alias your domain. So those resources can be served from locations that are closer to the users. I'm gonna skip these because it's very, very abstract, but I can come back to this later. And this is so this is a picture of our system. It's actually 2 years old. If you want to read about it, there is a page at the bottom. We deal with the Twitter Firehose, so we ingest all the Twitter traffic and a lot of other sources. So we have inbound traffic. There is anytime between 10 and 15,000 messages per second coming in. The way we designed this platform was to implement a service-oriented architecture. So each component there, each box can be scaled horizontally. Remember the N+1 principle at the beginning? So they have a nice interface. They are easy to to scale horizontally. So if there is a bottleneck anywhere in the system, we can just add one more box, simple as that. Even within a single service, there are a lot of ways to scale the way you distribute the workload. And one way is to use some kind of a job queue system. So you can take the load from the inputs and then distribute it internally to a number of workers that can vary with time depending on the needs. This introduces the next big topic I want to talk about, because I think queues are worth a special mention. I really like queues because they solve a lot of problems. So first of all, they are asynchronous. So the speed at which the consumer gets data out of the queue is not limited by the speed at which the producer is inserting data. So as long as there is something in the buffer, then there is no lock and wait state in the queue itself. They also help smoothing the traffic. Supposing you have an incredible spike that lasts a second, usually if you don't have any kind of protection, you risk losing that traffic. So you reject most of it. Or you put too much load on your system, so it crashes. So if you have a way of smoothing the traffic with a queue, that's a win-win. They also are incredibly effective at batching. And batching is the #1 technique to improve throughput. If done properly, batching can also help latency. This is a bit counterintuitive. You think batching will always increase latency, but it's not the case. At optimal speed, batching will actually improve latency. There are different ways, different patterns you can use queues for. So, as I mentioned earlier, they are very effective at load distribution, workload distribution, or data distribution. Supposing you have one producer, you can make it insert all the data into a queue, and you can have many consumers read data out of the other end. So you can have like units of work, they are buffered internally, and then at any time one of the workers can take load, they will simply pull one item off the queue and proceed with processing it. Or equally, you can have a multiplexer. So you can have many queues and collate all the results back into one node. So you can, with these two patterns, put like in a mirror configuration, you can have one producer, many workers that can actually do the work, and then you can collate the results back at the other end. Some queues, for instance, ZRMQ is one of those systems who allow this. They have some kind of a broadcasting system with subscriptions. So you have, for each message you broadcast, and hence is available to everyone that is listening, you can have a topic and then the actual payload. And certain consumers might be only interested in some pieces of work, pieces of data. So they will subscribe to the topic or the topics they are interested in, and all the other traffic is automatically discarded. If it's not interesting to anyone, then the data is dropped at the source. So some systems can do filtering at the producer end instead of dropping data at the consumer end after transmitting it. You can also use this technique for load balancing and work distribution across different data centers. So you can have a few publishers, and you can spread the load, spread the data, spread everything across different data centers, and have them just listen to the broadcast and subscribe to what they want. Taking the idea to its extremes, you could also think about having some kind of message bus for your entire platform. Supposing you are a system like Tumblr or a social media site, you might have certain events that need to be forwarded or sent to different parts of your application. Supposing you have, I don't know, an internal messaging system that allows you to send one message from one user to the other. That event has to be sent to the inbox of the other person. So that's a part of your architecture that will deal with the inbox of each component, each user. But there is another interesting party that could be the caching system that might need to invalidate the cache for that user upon the reception of that event. Or you might also want to send the same message to an email system. So the same notification that appears on the website is also sent via email. And that's the responsibility of a different part of your architecture. So if you have a message bus like this, where you pipe all your events, then you can have different components subscribe only to the bits that they are interested in, and they can pull the data out of them very easily. This is also very useful for both handling some downtime without losing data or traffic, or can be also useful to help load testing your site on a different environment rather than production. Because you can save the log, and you can replay all the actions on a different environment. So you simply rewind the pointer, you replay everything. So you can reproduce a situation that happened on a production environment elsewhere for debugging. Or in a production environment, you can have different parts of the system going at different speed, each with a different pointer to the buffer, so they can go at a different speed. For instance, the emailing daemon that sends all the emails doesn't need to be extremely real time. So it can wait a bit, let the system cool down a bit, and when there are resources, it will simply resume the reading from the buffer from earlier on, without affecting the point that the other systems that are reading from the same buffer are reading. So these are just examples of things that you can implement there. The last part of the talk is monitoring, and this is mainly a pointer to tomorrow's talk, because I'm going to show what you can do with monitoring dashboards and how you can reason about the way your brain works to make awesome dashboards for monitoring. Just a word in general about monitoring first. As I mentioned, you should enter this mindset of baking monitoring hooks into your application from the start for the reasons I already mentioned. And there are different questions you might ask at different times that require to have some insights from the application. So first of all, you want to know if there is a problem. And this is usually a question that is answered by business metrics. So for instance, you have a reduction in number of newsletter subscriptions. You might wonder why. So you keep investigating. You know there is a problem. You saw a reduction in traffic. And then you go to the next level. You try and understand where the problem is. So this is where system monitors are useful. So you check whether the database server is overloaded, whether you have enough bandwidth or not, whether there is a CPU or memory bottleneck. And finally, application monitors, those who you put in place in your application, will tell what the problem is. So hopefully you know how to think about what are the vital parameters for your application. You can monitor those. Be aware you don't want to generate too much traffic, because it could drown the system, or the monitoring system itself could be the bottleneck. So there are a lot of ways you can do it to have this monitoring system be really effective without bogging the system down. There are a lot of tools. Most of them are open source, and they are really good at different things. So specialization in this case is really good, because you can monitor different things, have different kinds of notifications for different parts of the system. Cover everything you can with metrics. Instrumentation is really essential. And you should have like walls covered in monitors that show the state of your application at all times, because you don't want to wait for customers to notify you of problems. There are a lot of types of dashboards and ways you can represent the state of the system. And again, this is just a teaser for tomorrow's talk. If you want to learn more about scalability, which is not, as I said, just about technology, but is equally about people and processes, I can recommend this book, The Art of Scalability. It's written by the architects of eBay and other very popular sites. It's really good. And there are other links there. You can download these slides from my site later on. Any questions? Nothing? Well, if you have questions, maybe about specific implementations, specific technologies that I've experienced with, please drop me in the corridor. I'm around for the entire conference. I don't bite, so don't be shy. And in the meantime, thanks a lot for listening to me.